work the next example, we need to discuss a couple of concepts. The first is the standing wave ratio. Now remember we said that you have both incident and reflected waves that occur in medium 1. And so what happens is you get a transmitted part that is a traveling wave in medium 1, and then you get a standing wave part that is a result of the superposition of a portion of the traveling wave with the reflected wave, which yields a standing wave pattern in medium 1. And so you can define what is referred to as the standing wave ratio, and that would be 1 plus the absolute value of gamma over 1 minus the absolute value of gamma. So the first thing to say is that if two materials have equal impedances, then gamma is equal to 0 and the standing wave ratio is equal to 1. So in other words, there is no standing wave. The wave fully transmits from media 1 to medium 2 because there's no reflection. The other case would be if medium 2 is a perfect conductor with eta 2 equal to 0. Then that would give you gamma is equal to minus 1 and S is equal to infinity, meaning that the wave is completely reflected. There is no transmission, and so all you have then on the left-hand side is a standing wave. You have no propagating wave. So let's keep this definition in mind because it's addressed in one of the problems. And then the other thing to discuss is that you will have, based on where you're on the wavelength on the wave, you'll have a maximum and minimum field value in medium 1. So you've got this propagating wave and reflected wave. They interact with each other, and you can determine from some geometric factors the location of the point where the value of the field is at a maximum. And so that's going to be the phase of the reflected angle plus 2n pi over 2k1. So we will utilize that in one of the problems, in the problem that follows as well. So this is just from some trigonometry, and then basically if your reflected angle is less than 0, your phase is less than 0, then n is equal to 1, 2, and so on. If it's greater than 0, then n is equal to 0, 1, 2, and so on. So in other words, you have some peaks, and you can find the location of the first peak from this expression. Okay, now let's look at the example problem. So we have a beam of yellow light that has a wavelength of 0.6 micrometers. It's normally incident in air upon a glass surface, and the surface is situated at z equals 0. The relative permittivity of glass is 2.25. So we're asked to find the location of the electric field maxima in medium 1, the standing wave ratio, and the fraction of the incident power that's transmitted into the glass. So first, let's determine eta 1 and eta 2 from the values given. So eta 1 is free space, so it's just 120 pi. Eta 2 is basically free space, and then this epsilon 2 is epsilon r, epsilon relative. So we divide 120 pi by the square root of 2.25 and we get 80 pi. So from that we now have eta 2 and eta 1, and we can calculate gamma, the reflection coefficient. So now given the reflection coefficient, and theta of the reflection coefficient is minus pi, so let's go back and figure out where that came from. Okay, gamma, remember, is in general complex, and so we have minus 0.2, so that means we have a phase angle of pi because that's what gives us the negative sign, and we have a magnitude of 0.2. All right, so now taking our expression for the maximum, we can take lambda 1, which is 0.6. We have theta r, and when we plug in lambda 1 is 0.6, then we'll get the location of the maximum point. Okay, part B asks for the standing wave ratio. So we take 1 plus gamma over 1 minus gamma, where we're taking the magnitude of gamma. And when we look at that, we find that we get 1.5. Now, what fraction of incident power is transmitted into the glass medium? Basically, that's going to be the ratio of the transmitted power density to the incident power density. So the incident power density is given by this expression, This was derived previously in the previous lecture. And so we've got the magnitude of the field squared divided by 2 eta 1. And then the reflected would be the magnitude of the field squared divided by 2 eta 2 times the transmission coefficient squared. So when we plug all of that in, we see that we have then tau squared eta 1 over eta 2. And plugging into the formula, we basically then get that we have 0.96%. So 0.96% is the fraction of the incident power transmitted into the glass. So most of it, actually, which we know because we see glass is transparent. Okay, here's another example problem where we have at this time a metal surface. So we have a 1 gigahertz X-polarized plane wave that's traveling in the Z direction. It's incident from air onto copper. We're going to let the air to copper interface occur at Z equals 0. The copper has a relative dielectric constant of 1, mu relative is 1, and the conductivity of copper is given as 5.8 times 10 to the 7th Siemens per meter. We're given the amplitude of the electric field incident wave, and we're asked to find expressions for the instantaneous electric and magnetic fields in the air and medium. We're going to assume that the metal surface is at least several skin depths deep. So in medium 1, so this is a problem where we can't use K, we have to use alpha and beta. So in medium 1, alpha is equal to 0 because we're in air and it's a perfect insulator. No, it's lossless. Beta is K1 or omega over C, so that's going to be 20 pi over 3. Eta 1 is eta in air, which is 120 pi or 377 ohms. And lambda is 2 pi over K1, which is 0.3 meters. Now the next thing we have to check is we have to check whether or not copper is a good conductor at this frequency. So we look at 1 gigahertz, we look at the ratio of epsilon double prime over epsilon prime because that's our test. So we take our epsilon double prime over epsilon prime, and that's going to be sigma over omega epsilon relative epsilon naught. So when we plug in all of those numbers, we get 1 times 10 to the 9th, which is much, much greater than 1, which means that at this frequency, copper is an excellent conductor. So that means for our eta C2, we use the expression from that table in chapter 7 that is appropriate for excellent conductors, which is 1 plus j times pi f mu over sigma under the square root sign. So when we plug all of those numbers in, we get 8.25 times 1 plus j milliohms. So eta 2 is very small compared to eta 1, or compared to eta naught for air. So the copper basically is acting like a short circuit. So the reflection coefficient for all practical purposes is -1. So if we now set gamma equal to -1, we can look at the electric field in media 1. So it's the incident wave, and then here is the forward traveling wave, and then here's where we plugged in -1 for gamma, and this is the reverse traveling wave. So if you look here, you see that this is e to the minus jkz minus e to the plus jkz, and that basically, using Euler's formula, is j times 2 times the sine of kz. And same for h, we find that that's going to give us, basically, when we do that calculation and plug in for h, we get the plus sign, and then that gives us cosine of kz. So if you look at this figure here, this is an illustration of what the standing wave pattern looks like to the left of the conductor. So basically, it's no longer a traveling wave because it's no longer of the form e to the j kz. It's now of the form sine of kz. So if we now go back to the time domain and add e to the j omega t and take the real part, we basically will get the sine of kz multiplied by the cosine of omega t instead of cosine omega t minus kz. So it's not a traveling wave anymore. It's now a standing wave pattern. So what happens is you've got this standing wave pattern, and then in time, the intensity of the peaks is just going to go up and down, reversing back and forth. So almost analogous to, if you hold a string and another person holds the other end of the string, and then someone plucks the string, but it's bound at the ends, so it forms this standing wave pattern. It's going to change in time, but the peaks are going to stay at a constant location in space. So if we now plug in for the electric field value, we can get an expression for the instantaneous field. So this is what I was saying earlier. We're going to take the real part of E1z e to the j omega t, and when we do that, we get the sine of kz and the sine of omega t. The j part has gone away since we're taking real, and then the same is true here on h. We are going to get the cosine of kz times the cosine of omega t. So once again, this is a product, not a difference, which is, so in other words, product of sine and sine, product of cosine and cosine, not the difference of omega t minus kz. So that just means this wave sits here and oscillates back and forth. It has a constant distribution in space, where the peak, though, is oscillating in time. So kind of an interesting phenomenon that you set up a standing wave pattern, but that's essentially what has to occur because the energy can't propagate into the conductor. All right, the next thing to look at is to look at waves with oblique incidence. And waves with oblique incidence are where we obtain Snell's laws in optics. So I know a number of people take this class because it is a prerequisite for optics, and Snell's laws are important in optics, and basically they come from the incident, reflected, and transmitted waves in electromagnetic fields. So what's different here is we have an incident wave and it's coming in at an angle, hitting a boundary, and then reflecting, and also transmitting. And when it reflects at an angle, and when it transmits at an angle. And so we define a theta reflected, which is going to be the angle that the reflected wave takes, and we define a theta incident, which is the angle that the incident wave takes. And I want you to note that the boundary is actually the xy plane occurring at z equals 0, but the reflected and incident angles are measured from the normal to that. So we do not measure the normal between k and the plane. We measure the normal, or we measure the angle between the normal to the plane and k. So that can be a little bit confusing. So basically, angles of incidence, reflection, and refraction come from Snell's law. This comes from applying the boundary conditions of electromagnetic fields. And so in Snell's law of reflection says that the incident angle and the reflected angle are equal. And then Snell's law of refraction says that the sine of theta t, which is the sine of the transmitted angle, divided by the sine of the incident angle, is the square root of mu1 epsilon 1 over mu2 epsilon 2, which is the phase velocity in media 2 over the phase velocity in media 1. So in other words, the angle of reflection equals the angle of incidence, and for refraction, sine of transmitted and sine of incident is expressed in terms of the phase velocity ratios. For non-magnetic media, we can define N, which is C over U, and so that would be mu epsilon over mu naught epsilon, or the square root of mu r epsilon r. And we can rewrite Snell's laws in terms of N1 over N2, where N is referred to as the index of refraction. For non-magnetic materials, where mu relative 1 is mu relative 2 is 1, then we have the sine of theta transmitted over the sine of theta incident is N1 over N2, which is also, by the way, eta 2 over eta 1, or epsilon relative 1 over epsilon relative 2. So these are important relationships, especially when you get into optics.